So welcome everybody to our NGTS seminar today. Today we are honored and pleased to have Dr. Sabya Mishra with us. He'll present his latest research findings on optimal rebalancing and matching strategy for autonomous and human-driven taxi fleet using reinforcement learning. Dr. Mishra is a Fadri Associate Professor in the Department of Civil Engineering at the University of Memphis, and his research interests are on impact of emerging technologies on transportation planning and decision-making, transportation economics, safety, and public transportation. So with all that said, thank you so much, Dr. Mishra, for being with us today, and the floor is yours.
Thank you. Thank you so much. So good afternoon to all the participants. I'd like to thank University of Michigan, everyone who were involved with this for giving us the opportunity to present this work. What I would encourage before I begin is that I will switch off my video during the talk, but I'll switch it back on during Q&A session. What I understand is that this is a kind of a group that is a diverse group, but many of the participants are typically students, which are because this is a series that is part of a class, but there are other interested participants as well, which are a bigger group of TRB. So what I would suggest is that, yeah, please, feel free to stop me if there are questions or anything you'd like to ask in between, or write down your question and ask towards the very end. Either way is fine. So let me kind of begin my presentation. All right. I'm hoping you were able to see my screen well.
I can't see screen again. I think
you cannot see again? Okay.
Maybe it's just me, but I see that you have started sharing your screen, but I just can't see the screen.
Okay. Maybe it's the same problem that what we're having before. Okay, stop sharing and let me try to rejoin and reshare.
Okay. Yeah, we can see that, but we can't hear you. Can you please unmute yourself?
Yeah, you can see the screen and hear.
Yeah. Now it's
okay.
also. Thank you.
Perfect. Thank you. Okay, apologize for the inconvenience. Yes, so to begin our discussion for today, the topic is on optimal dispatching and repositioning strategy for autonomous taxi using reinforcement learning. I would begin the presentation by mentioning that this is the work of my PhD student, Juan, and Juan is also attending today's session. And this work is part of his doctoral dissertation. This is kind of a work in progress that is not fully published, but it's communicated to a journal. So that's kind of a good fit for essentially presenting in today's session. So what we expect for participants to learn at the end of today's session is that we will be talking about and learning more about the role of taxi in situations where we have imbalance in supply and demand. And we will be looking into autonomous and electric taxi. That's what AET stands for. and AET dispatching as well as repositioning framework, how we can formulate a problem where we consider autonomous electric taxis, their dispatching and their repositioning. And we will also look into learning more about use of optimization and reinforcement learning in autonomous electric taxis. We will also look into how we have approached as what could be a potential solution algorithm, as well as we will look into learning from this case study. So what we see here is that technology provides a better tool to perform any new task that we carry out every day. Over time, we see that a lot of technologies which existed in the past are replaced by newer technologies like typewriters to Word, or the old types of phones to smarter phones, or calculators, or beads type of things to things like Excel or other programming languages. Similarly, what we see is that the regular taxi or human-driven taxis, which used to be solely operated, are used by ride-sharing companies such as Uber, Lyft, or other companies all over the world. So technology does provide us a better tool to perform the task that we carry out every day. So what does that mean? So that really is needed because we have TNCs as well as solely operated taxis. Those coexist in our urban setting today. That creates the first problem that's what we refer here as spatial imbalance. So this is a figure, what we see that is related to taxi pickup density in New York City. What we see here is the underlying network, which is the New York City network. And it represents taxi pickup density in New York City. That means brighter are the links. That means the density of taxi pickup is greater and greater or higher. So those who are familiar as well as those who are looking at this network, we know that there are three major cities in this picture. The north part is Manhattan, and the eastern part is Queens, and southern part is Brooklyn. Those are the three cities that are individual kind of, we can say, central business districts within the bigger metropolitan area of New York City. So what we see in Manhattan is that very high demand, as we see in the type of brighter colors of the network, whereas what we see in Brooklyn and Queens is lesser demand. So what this does is that really creates an imbalance between supply and demand. Demand is very high in certain areas and low in other areas. So the question that really is in our hand is that how taxi companies, taxi drivers, or a central controller like a TNC, if it can be in the future, how do they manage this supply and demand imbalance? So that's what we see here. The demand for Manhattan is much greater than that of Brooklyn and Queens. And if taxi supply is the same, then the question that remains is that there would not be enough taxi in Manhattan because the demand is so high. And as well as there will be surplus taxis in Brooklyn and Queens. Unless taxi drivers learn from their daily behavior or daily demand pattern, they position themselves elsewhere. So what happens as a result of this supply and demand imbalance is that maybe the demand is not necessarily met appropriately, or the wait time is larger, or taxis unnecessarily move along the network for a longer time period. So that's what we refer here as spatial imbalance in terms of meeting the demands by taxis on the network. So is this imbalance only applied to New York City? Not necessarily. I would say this imbalance is applied to any urban city or any urban area that we can think of. So this type of imbalance would occur. In addition to spatial imbalance, what we also see is temporal imbalance, meaning by time. We all know the daily distributions of our trips So this is an example of what we see, what happens in x-axis in 24 hours of the day, and y-axis how traffic volume varies by different type of days of the week. We do not see that. We do not expect. We all know as traffic engineers is that demand varies over time, not only just during the time of day, but also by day of the week. So in addition to when we couple spatial imbalance with temporal imbalance, that really becomes a complex problem. So in addition to spatial demand, we have temporal demand. So in combination of both spatial and temporal imbalance, that is something providing supply for required demand essentially becomes challenging for us. So to meet or to somehow address this problem, what taxi companies are doing is essentially have allowed the surge pricing concept. So in surge pricing concept, so transportation network companies, say Uber or Lyft or other companies, they introduce surge pricing. So what it does is that it multiplies the normal price in high demand areas, especially central business districts or downtown areas, and with a very few taxis nearby, because they see that demand is very high. So now there is an opportunity to increase kind of willingness to pay, to really test how much people are willing to pay by increasing the price, because there are only very few taxis to serve and the demand is very high. So what surge pricing essentially does is that it attempts to persuade drivers to accept trips from which are much farther from them. For example, a driver typically does not drive more than 20 miles, but now sees a lucrative trip which is 20 miles away, then the driver is willing to accept that offer because it provides more incentive to the driver. That is what the driver is doing. But what happens as a result is that it might be the case that the customer who requested the trip by expecting the delay can cancel the trip as well. That unnecessarily increases the trip length, which is not good in terms of network usage. So what this surge pricing does is that unnecessarily increases the fare. And this is an article from USA Today that how much time, like a 9-fold, 10-fold increase of the price than the normal fare. That's what surge pricing does. So surge pricing has kind of limitations as well, as spatial pricing can reach price equilibrium at a higher level. Higher level meaning here, as I was referring here, is that willingness to pay from a customer side really is tested here. How much are you willing to pay? Are you willing to pay 9 times the normal fare to really request a trip? So equilibrium meaning that point where the customer as well as the driver or the TNC essentially meet that they're mutually agreeable to a specific price. And that price is much higher than that of the efficient levels. So what surge pricing does is that it has a small positive impact on the driver's decision for accepting trips which are far away. But it introduces a lot of negative impact on the customer's decision on whether to cancel the trips or not. That is a challenge what surge pricing does in terms of network usage as well as meeting the demand with limited available supply. What we can see as one of the solutions to this demand and supply imbalance is repositioning. So in repositioning, what we are talking about is that if we look into the 3 cities or 3 kind of different downtowns in New York City, Manhattan, Queens, and Brooklyn, what we can think of is that let's move some of the taxis from low demand areas to high demand areas, but we can do that preemptively. So if that is the case, the question remains is that how preemptively this can be done, how preemptively we can do this. The question here comes is that, can this be somehow done autonomously? Meaning autonomous electric taxi, will that be an option? So the question we are referring here is that, smart repositioning can really solve this supply-demand imbalance. Smart meaning somehow automatically, if we can do this type of repositioning, meaning realigning the taxes in locations where there is demand. So what we're referring here is that a central controller can include really this concept of repositioning in its plan. So if that is the case, then what is going to happen? So we can move vehicles from low demand areas to future potential high demand areas. So that is what repositioning can do. So in what we see as another challenge here is that autonomous electric taxis are not going to be containing 100% of the market. They will have to operate initially with human-driven vehicles as well. That means we will have a situation where autonomous electric taxi and human-driven vehicle, they will be operating simultaneously. So the question that remains is that in a mixed environment where we're talking about autonomous electric taxi and human-driven vehicles, how TNCs can dispatch the vehicles, how dispatching system will look like. So what we're referring is like a company such as Uber, which currently has human-driven vehicles that various drivers are employers of Uber who are operating manually, meaning they are the drivers, they have their own vehicles. So it's a human-driven vehicle. But in future, we're talking about autonomous taxis with no drivers. But they can come from various different type of companies, such as in this example, Uber do not need to essentially own a vehicle to be part of its fleet. It can come from Waymo or any other companies. The question is that when we have two different type of vehicles or two different type of kind of taxis operating, one is human driven, other is autonomous, how we should prioritize this dispatching of these taxis or preemptively repositioning these vehicles in this mixed environment. That is what essentially is the question that we're asking. So in addition to what we talked about, two different type of vehicles, there are challenges in terms of infrastructure usage as well. For example, it could be the case that specific links or specific lanes can be only designed for AV specific lanes. That means only autonomous and electric taxis can use those lanes, and human-driven vehicles cannot use those lanes. So there could be dedicated lanes for operation, as well as that there are specific charging locations that AETs, autonomous electric taxis, likely to be using. So they might not be charging the entire day, but parts of the day they need some time for charging. So that really also adds the complexity that when we want to reposition those taxis, we also need to account for how much time they would be taking for charging. So in this regard, what becomes a research gap is that in the previous studies, what we have seen is that there are a number of studies which are people have analyzed this problem as a zone-based, meaning take a study area, make number of zones, but do not consider node-based, because pickup and drop-off, in reality, pickup or drop-off or vehicle location is at the node level, which is where the passenger is, not necessarily at the zone. So for example, one would say that if it is zone-based, someone can say, I'm in Midtown, versus if it is node-based, one will say that I'm precisely at this location. So at an intersection. So that's the difference in reality, that what challenges can happen if the precise location is zone-based versus node-based. So that is something that needs to be addressed, number one. Number two is that now we need to consider simultaneously strategies for autonomous electric taxi and human-driven vehicles together, such as the concept of carpooling and repositioning. And also we're talking about a mixed fleet, not just distribution of existing supply. That means we need to precisely identify where the location of the vehicle is, what is its status, and what is its itinerary, so that we can appropriately adjust whether a specific vehicle is ready for pickup or not, or what is its status. So those are some of the research gaps. So what we identified as an objective of this research is that we wanted to develop a framework. Again, this is a framework, an initial framework, to essentially optimally dispatch both human-driven vehicles as well as autonomous electric taxi. We want to make sure that we can also analyze their repositioning and recharging of autonomous electric taxis, because they need to recharge. And also we need to simultaneously minimize what we call as customer wait time. If a customer would be canceling, there should be some sort of a penalty for cancellation, some operational costs of autonomous electric taxis, and essentially kind of introduce a penalty for AET undercharging, meaning if the vehicle is not fully charged, that means it will not be able to serve. It should have sufficient charge so that it can meet the customer demand. Otherwise, the vehicle will be stuck. So there should be some sort of penalty for that as well, to address kind of range and anxiety in the last bullet. So to consider or to fulfill this objectives on this slide, what we have is an overall kind of a framework that we're going to present in the next few slides. So here we begin with kind of defining what is our network. So we represent our network as a graph in which each intersection is a node, something that is classically represented in a graph, as well as we represent road segments or links, and links are nothing but kind of lines connecting these nodes. Then we're talking about if a taxi's location is in the middle of the segment. If that is the case, then what we do is that we approximate its location to the nearest node, that where it can really pick up or drop off a customer, what would be the nearest node, not just necessarily at the middle of the link. Then what it does is that this approximation we use here, this significantly reduce kind of things such as computational complexities of exactly identifying which is the nearest node. And we also introduce the concept of taxi zones. It's not necessarily that we don't have taxi zones. We have taxi zones because that's what in reality that will happen. But essentially our pickup, drop off, and those happen essentially at node level, not just necessarily at zone level. So what taxi zones does is that it facilitates matching between a driver and a customer. And also it can reposition of taxi between zones. It can, because there is availability of charging or no charging based on that, it can position itself in a specific zone. That's where taxi zones are needed. But the complete formulation is still node-based, even though we recognize and incorporate the concept of taxi zones. We still work at node level, where we do consider vehicle location, its complete itinerary, as well as pickup and drop-off locations. So if we extend the methodology, then in addition to considering the network, now we will be looking at the temporal setting, meaning how we consider different type of demands throughout the day. How do we consider time considerations that comes next, in addition to the spatial consideration or the infrastructure, what we looked at in the last slide. So in temporal setting, we can consider, for example, let's consider a day. And that day can be considered as an episode. We can call that as a name as episode in this paper or in this work. Let's say we give that time as 6 a.m. to 8 p.m. Not necessarily these are time constraints. The user can really define what a duration is consisted within an episode. Then what we do is that we discretize essentially an episode into small time intervals, but those intervals, we keep them as equal. For example, every 5 minutes. So throughout the day, we can discretize the time into every 5 minutes so that whatever times we have, we know exactly what are the discrete intervals within an episode is. So let's look into what is an episode a little bit more. So the definition of episode that we introduce in this is that an episode starts with a first timestamp or a time step, and the controller gathers the vehicle's state. So what do we mean by vehicle's state? The vehicle state means where is it located, which taxi zone it is, what is its status, what is the charge, how much level of charging it has, as well as if it has any plans or not, itinerary-wise. And demand request within a time step is kind of, we aggregate it and process at the end of each time step. We also look into vehicle fleet setting. How many vehicles are operating? We need to have some sort of an idea. So TNC manages kind of a fixed amount of fleet. So we consider that also as an input. And human-driven vehicle supply are drawn kind of from, if we have some data related to historical distribution, which can vary in spatial and temporal dimensions, we consider that. But AETs can do single pickup, carpooling, repositioning, and recharging. Those are kind of specific to AETs. But human-driven vehicles only do single pickup. And after the trip is completed, the human-driven vehicle will log off the system, or meaning after it's completed, it's ready to essentially take another trip after completing one. So those essentially are the difference between HV and AETs. So this is the methodology begins with starting an episode, and within the episode, what is the time, discretized time interval. So that is what we begin in the first step. From the first step, now we move to something called as a process. There are 4 processes that we're going to talk in the methodology. Let's begin with the first process in this slide. So after we begin a timestamp or a time step, it updates the vehicle state and gather demand request in the next 5 minutes period. What is happening? It looks into the next timestamp. Then in this slide, we will talk about module 1 because it consists of modular processes that we're talking here. In the module 1, module 1 tries to match requests with human-driven vehicles and autonomous electric taxis for single pickup. Again, the importance here is single pickup. Then let's quickly look into how we are formulating the problem. I'm not going to go very deep into the formulation. I will try to give a general idea of what we are essentially doing here. So we have a decision variable that really is a binary variable, and it takes the value of 1 if the vehicle picks up a specific request, or if it does not want to pick up, then essentially takes the value of 0. Then we have an objective function, and the objective function is matching, again, the demand with human-driven vehicles and any type of autonomous electric taxi that is either idling or repositioning in the same zone. So that's what process 1 or module 1 is trying to do. The first component of the objective function is a penalty for any missed trips. The second component of the objective function is the total pickup time. And the third part of the objective function is waiting penalty for the human-driven vehicle. So these are the 3 components of the objective function. Then with that, we kind of move to different type of constraints. So we already looked into the objective function. Now let's look into what are some of the constraints of process 1. So in combination, the second and third equation, or the first and second constraints, it says that taxis, which includes both human-driven vehicles and autonomous electric taxis, in the same zone as demand, they're either idling or repositioning, is eligible for matching. And if it is an autonomous electric taxi, then we assume that it has enough range. Then only it becomes eligible. If it does not have enough range, then it does not become eligible. That's what equation 2 and 3, or the first 2 constraints, refer to. The next constraint refer to penalty of not serving a customer, which is the average pickup time of eligible taxi and plus the customer's wait time. Then a taxi can be served at most 1 customer in the process because this is single pickup. and a customer can only be served by at most one taxi. So not many taxis are serving one customer. And lastly, essentially a decision variable that is binary, as we talked about, whether it is a serving demand or not. So it takes a value of 0 and 1. So that is essentially module 1 or process 1. So after completing process module 1, then we essentially see if there is any unserved demand or not. If there is unserved demand, then we look into module 2. What module 2 does that it looks for potential for carpooling pair, and it matches the request with single pickup taxi in the same zone. So carpooling is something that we consider in module 2, and it has 2 terms. And the first one is penalty for any missed trips, as well as how much is the pickup time. And then there are a number of constraints here. So we will not be essentially going very deep essentially into a number of constraints, but the constraints essentially are telling that if some of the conditions are concurrently satisfied, then essentially we include that trip or add that carpooling trip into the overall number of vehicles served. So this includes, for example, whether one request is fulfilled or not, whether there is enough range or not, what is the total trip time for both passengers. So those are essentially the things that we consider. So the objective function here in process 2 is minimizing the pickup time and penalty of those are unserved demands. So it encourages carpooling in module 2. Now we look into module 3. So in module 3, what we look into is that we essentially provide a criteria for carpooling. And also we essentially look into demand that is served from process 1. If it is the case, then it does not need to be processed again as a constraint. And by looking into both process 1 and process 2, we need to update the demand. So we update the demand serving status of the following equation. So yes, this is, yeah, that is correct. This is still module 2 that we are talking about. So updating the demand serving status using this following equation here. Let me see here. Yes. Now what we do is after module 2, we essentially go to module 3, that is to match the request with available or available. In module 3, we match the request with any available or repositioning autonomous electric taxis in any adjacent zones. So this matching of idling and repositioning taxi in adjacent zone. So what we are talking about here is that there's a penalty for missed trips and there is a pickup time. And what we are referring here in terms of our constraints is that the vehicle is in adjacent zone, and whether the vehicle is idling or there is a limitation for pickup time, as well as it needs to have enough range. So these are the constraints which were kind of explained in the previous slide. And demand not served from process 1 and 2 can only be served here in module 3. Now we come to the next module, or the last module is module number 4. So we talked about till module 3. Module 4 is repositioning of taxi between zones. So based on the environment at play, so the vehicle will take an action, how many taxi to reposition between zones. So we need to select a taxi to reposition until the quota is met. So what do we mean by that? So in process 4, we talk about while meeting the demand in process 1, 2, and 3, we talk about repositioning and recharging in process 4. So in process 4, an agent interacts with an environment by trial and error, or use the feedback and experiences from its own action. And then we need to understand what is the state at play. And the state is the agent is currently in, and it has information about what type of action it would need to take. That would be the state. An action is essentially the agent takes an action, meaning such as essentially whether to accept or not, meaning whether to reposition or recharge or not. And based on that action, it will receive some sort of a reward. And we update the state based on action of the agent. And what is a reward? A reward is nothing but an agent receives kind of a reward each time it takes any action. So what is the objective of the agent? The objective of the agent is to maximize the overall reward or cumulative reward at the end of the episode. So whatever would be the episode, for example, a total day consists of each 5-minute period, it would like to kind of maximize the reward from each time period to each time period for the entire day. So what happens here is that there is an agent essentially state. We know the state of the agent. An agent essentially takes an action and receives an award based on the environment that it is in. So to address that, what we have here is that we have different states, such as we have unserved demand, number of idling vehicles at each zone, and how many number of vehicles those are available, and any type of demand that we have historical, and how many vehicles are in undercharge. So considering those, what we try to do here is that the model is immediately taking an action to reposition and recharge. That's what is this XIJ repositioning refers to. Of A, it is where essentially it's a matrix where rows corresponding to start of the zone and columns represent end of the zone, plus one additional column that is given for charging. So if we kind of look into a matrix, then we look into essentially a kind of a square matrix that is for repositioning, and one additional column that refers to what is the number of charging. And then the next two equations, that 18 and 19, are percentages of idling vehicles. And what we identify in equation 8 is a percentage of repositioning vehicles, and 19 is the number of vehicles needing essentially charging. So after that, we identify what is the state of charge. If we want to calculate for each vehicle, that would be the ratio between what is the remaining range and how much distance it can travel. So if the state of charge is greater than 1, then it can easily serve and it does not receive any penalty. But if state of charge is less than 1, then the vehicle, which is autonomous electric taxi, does not have enough range and it cannot essentially reach to the nearest charging station. So it will be defunct for rest of the operating day if the state of charge is less than 1. So if this happens, then we would incur a penalty in the reward function. And what is that penalty in the reward function? We'll talk in about a few slides. So in this framework, what we're talking about is this is a vector, charging vector, which we saw in the previous slide, that autonomous electric taxis that have, we can essentially arrange them in ascending order, like how much charge do they available and how much is the distance that they have to the nearest charging station. So we talked about reward function and what would be the reward function. First, the reward function will be a negative value, overall reward function, where the first term is about the customer wait time. And second is the cancellation penalty. Third is what is the cost of repositioning. And the fourth one is that penalty for undercharging. Those would be the 4 components of the reward function. So what is the goal of reinforcement learning? So we're talking about still the approach, but in this, we will be looking into reinforcement learning as one of the solution approaches. So here we're trying to develop a function that, given any input that is state S that is given to us, it will lead to an action that will maximize the cumulative reward. So that means for each time step, there is only one optimal strategic action or the output. So for example, the input is the state, and we have a function, and we have an output. The output is the strategic action. So we need to understand a little bit more what is the function. So this function, we refer to that as a policy function, and which consists of two parts, which is state of charge, as you see ST, and a parameter that is theta. And policy functions can take many different type of forms. And in our case, we kind of used a parameterized neural network to describe this policy function. And the objective is for us to find the weight of or biases of this parameter of this neural network to maximize this cumulative reward. And this is what we maximize as a function to get the desired or optimal strategic action. So this is how the policy function neural network is strategized. So we have essentially future vehicles, idling vehicles, unserved demand, historical demand, and undercharge. And here what we do is that we essentially convert the matrices into different forms. So for example, the future vehicles and idling vehicles, depending on their dimensions, we can essentially convert them to how much would be the outgoing vehicle. For example, here, z times t and z times 1 will give us z times 1, and then we can essentially concatenate it, and that will be fully connected z times 1. Similarly, we have unserved demand, historical demand, and undercharged vehicles also accordingly arranged to how much would be the incoming vehicles. And then essentially we use matrix multiplication to identify what would be essentially this policy function. That's how the policy function is kind of defined. What it will have, the dimension is z times z plus 1. We'll talk about that in just a few minutes. Again, we talked about the left repositioning matrix is a square matrix, number of rows and columns are equal, but an additional column is added to this matrix that tells about number of charge. So here what we are talking about is after finishing the methodology component, we talk about solution algorithm. The solution algorithm that we used in this paper is referred as A3C. And here, the 3 A's that we talk about, the first is asynchronous. That means the environment is simulated simultaneously on multiple CPUs. So any knowledge that we gather that are updated and shared between all CPUs. It's not that any CPU is advantage over other. So pictorially, if we try to represent this algorithm of A3C, we have a global network that has a policy function. It has a network and state of inputs, and number of CPUs are here, and each CPU is in a separate environment. And they essentially, we simulate this environment simultaneously in multiple CPUs so that we can update their state accordingly. The second A refers to advantage. That means how good an action is compared to other alternatives. And the third one is the concept of actor and critic. So there are both of them are involved. An actor is telling what the agent should do, and a critic is telling how good the action actually is. And the policy function incorporates both the actor and critic's viewpoint. So the asynchronous concept, advantage, and actor critic concept together really forms the solution algorithm. To compare our strategy, what we are proposing, we also incorporated something called as manual allocation. In manual allocation, we introduce a strategy for comparison purposes and validation purposes that what we are proposing in the AET framework of the 4 modules that we talked about, is it any better from manual allocation? Like someone does allocate the taxes to meet the supply and demand imbalance manually. Does it any better? So to do that, we have the manual allocation strategy. So here we match the taxi demand with the closest taxi, and there's no repositioning or carpooling. So if we condense the 4 processes that we looked into, or 4 modules, manual allocation is nothing but just process 1, where the vehicles are just matched with the demand. And there is no concept of carpooling, there is no concept of repositioning and idling, no concept of charging, so on and so forth. So to essentially test the framework, what we have is we took a network. I think many of our participants would be familiar about Anaheim network. This is the Anaheim network. What it has is that we have 15 taxi zones, as you see here in red. So if you see each of the kind of the squares, that means they are each individual taxi zones. We divided or created these imaginary taxi zones. And the network consists of kind of AV or AET enabled link, as you see here in blue, as well as kind of HV only link, and that is colored in black. And then we have charging stations hypothetically provided over the network. So what are some of the salient features of the network is that it has 940 links and 416 nodes. We created 15 taxi zones and 12 charging stations. And our fleet size we considered is 400. And there are 760 requests at peak hour, though these requests vary by time of day as well as day of the week. So if we look into the given demand, this is the input data. If we represent is a matrix, we can see from which zone to which zone, essentially there is more demand. So there are 15 zones here, taxi zones. So from and to zones, we can see, for example, 1 to 2 is one of the very high demand states. And here we see the variation by time of day as well as day of the week. This is, again, an input data that really goes into the model. So what we do here is that we're training the model for 175 episodes. That means we're assuming that we have 25 weeks of data, and demand varies by day. And we plot it in separate series where we have wait time, cancellation time, operational costs, and we try to essentially maximize the reward using reinforcement learning. The question is that we need to convert the cost into negative values. That's what the reward is. So what we see here is that the reward increases steadily at each episode. So let's look at that in a graph. So a few things to consider in this graph is that each of the graphs, there are 7 graphs, 7 sub-figures in this figure. Each figure represents a specific day of the week. And then x-axis represents what is the training week. That means you can consider all 25 weeks of data is presented on x-axis. And y-axis is the total reward function in 1,000 minutes. As we saw that the reward is, we purposefully took that as a negative value. What is happening that with learning from day to day, the value of the reward is increasing. And for each day, it's not necessarily stable. That is what we would expect a learning function to provide us. And that's what the reinforcement learning is giving us is that the reward increases steadily at each episode. And if we look into training by wait time and cancel trips, then wait time and cancel trips, we see that they're steadily decreasing as the model is kind of learned more over time. So wait time shows drop than cancel trips. Let's see this in this figure. So what we see in this figure is that the number of weeks here, we see here 25 weeks, and x-axis is the wait time in 1,000 minutes. And this is what the columns represent in this graph. And the line represents the weekly cancel trips. That is also in 1,000 trips, though the magnitudes of primary y-axis and secondary y-axis are different. What we see is that as the model is learning from one day to other day and so on and so forth, then we see that the wait time is decreasing. It's not remaining constant. You see that the wait time is significantly lesser towards end of the time period of 25 weeks. And the number of canceled trips are also steadily decreasing. That's what we would expect, and that's what is happening. The next one is about weekly dispatching and repositioning. This figure really talks about, again, the x-axis is the training week, y-axis is weekly dispatching via single pickup, and that is the columns. The columns again have 2 parts. One is for repositioning, other is recharging. Repositioning is more because vehicles reposition more often than the number of times they charge. So charging numbers are usually small, what is expected. And in addition to that, we are talking about essentially the single pickup as well as carpooling. That's what we see here. The dotted line is for carpooling, and which is lesser than the single pickups. Single pickups are much higher. So this is from the TNC viewpoint, because they would like to see the dispatch as well as repositioning. So what we see here is that more repositioning results in more single pickup, and carpooling remains stable because there are certain criteria only for carpooling, and charging also remains stable because the weekly demand is kind of more or less the same, even though they differ slightly from day to day. So to essentially apply the model, we utilize a data that is a new taxi data that is not used in training. And we consider 50 days or 50 episodes, followed by spatial and temporal variation. And then as the training data, what we see here is that this is manual allocation. We do not see a significant or a continuous decrease in terms of wait times. That is what we see here as the columns. And the lines are number of canceled trips. They also kind of oscillate from time to time from the episodes or the days over the 50 days. That's for manual allocation. What happens in using reinforcement learning is that if we look into the autonomous taxi dispatching systems that we proposed in 4 modules, the wait times compared to that of the manual allocations are significantly lesser, as well as the number of canceled trips are also significantly lesser. We did keep the values of the primary and secondary y-axis are same so that we can compare what is happening. So what is the observation? That there is a pattern with a period of 7 days showing the demand variation, and autonomous taxi is able to essentially do this quite significant and efficiently compared to manual allocation. I see that my time is kind of about 50 minutes. I'll try to wrap up probably next 5 minutes. So here we see that on an average for the entire 50-day period, what is happening in terms of average daily wait time for manual allocation as well as autonomous taxi. See, what we see that for autonomous taxis, we're able to reduce the wait time about on an average over 70%. Similarly, for canceled trips, daily canceled trips, we're able to improve the number of canceled trips also over 70%. This is essentially an average table of the previous slide where we showed the overall what is happening for each of the episodes. So again, it's about waiting time is improved by 75% and canceled trips by 73%. Now, if we're talking about idling time, then we can compare what is the idling time. So what we see on this slide here is that this is the repositioning matrix that we take. And then what we see, number of vehicles and total demand. So demand is kind of more or less in certain instances higher, certain instances lower than that number of vehicles. So what we see here is the comparison between manual allocation and the AET framework is that the idling time in the manual allocation is much higher. As you see here, number of red blocks are much higher. Compared to, we do not see kind of a dense red block on the AET framework, which essentially where we're able to use the concept of reinforcement learning. The essentially idling time is much more reduced in the AET framework. If we look into 1 day of the entire fleet, then what is happening? We see in manual allocation, here you see is that how many number of pickups being made. The darkest color is above 194 pickups. And if we see, probably we see about 3 or 4 type of such nodes, as well as we do not see many darker nodes for manual allocation. That's for 1 day entire fleet. But in the AET framework, you see that the darker number of pickup points are many, many higher. That means we're able to pick up much efficiently compared to manual allocation. If we look into one vehicle, what it does, we see that, you know, for in autonomous taxi or AV framework, the vehicle is repositioning itself, fulfills many times the customer wants need, also uses carpooling. It does picks up and dropping off customer. So we also show where does it start, where does it end, and where does it charge during the day. As we see here that this is the location where the vehicle essentially charges. And the AAT framework says that it essentially serves 33 customers. In comparison, if we see here, essentially the manual allocation does not do carpooling, and many of the pickups are only single pickups. Not necessarily many, does not include carpooling, and also serves less number of customers in manual allocation. If we would like to see what happens one day in life of a vehicle, this is what we see here. This is the legend. What we see that what the vehicle is doing, fulfilling the customer, then does it do carpooling or not, picking up a customer. What you see here is some sort of delay. That means it is resting here and it will begin its work. As you see here, essentially it began its work after resting. And we can also see where it is picking up. So in manual allocation, that's what it is doing. We do not see any kind of fulfilling customer to here. We will kind of move now to, for AAT framework, we see here is that essentially there is a lot of changes happening compared to that of the manual allocation. This is what is happening, how all those 33 trips are made, where reposition, where carpooling happens. This is what we are showing in an entire day for one vehicle. So, all right. So if we look into one day, one vehicle, what we see here is that for manual allocation, this is what is happening for the entire day. So from 6 a.m. to 8 p.m. is what we consider, in which how many times the vehicle is doing single pickups and how much, where it's charging in manual allocation for those 25 trips. So what it is telling is that maybe this is a case where one single pickup is completed. But in this case, actually, it took 2 5-minute intervals to complete the trip. In this case, probably 3 or 4 time intervals, here 1 5-time interval, like that. If we count kind of the consecutive lines that it has together, then those will be 25 number of trips those have been being made for manual allocation. For autonomous taxis, what we see here is that other type of activities are involved, such as repositioning, carpooling, charging, and what it does, it does serve 33 different number of trips. So in conclusion, if we kind of look into what the goal of the paper or the work was, that we wanted to analyze imbalance between supply and demand. We wanted to incorporate dispatching and repositioning framework. And we used single pickup and carpooling. That's for process 1, 2, and 3. And for repositioning and recharging, we used reinforcement learning. So those were the first 3 steps was just linear MILP was used, and for the 4th, repositioning and recharging is reinforcement learning. So in summary, if we look into what was our input, a fleet of autonomous taxis, and we looked at what is the customer demand, and also a given road network with taxi zones. These are all input data that we required. And what is the output is how to match the customer and taxi for single pickup and carpooling, how to reposition, the concept of where and when, we tried to answer that, and also how to recharge, as well as where and when, considering different type of or number of recharging locations. So what is the benefit of this work is that riders will experience shorter wait time and less frequency of canceling their trip, because a wait time would not be excessive, and TNCs can operate more efficiently, and we can consider both autonomous electric taxis and human vehicles simultaneously by considering the location, taxi zone, status, state of charge, and itinerary. Also, we can look into single pickup, carpooling, reposition, and recharging. There are some limitations of this work is that we were not able to do any more validation other than the manual allocation. We can do other type of validations given that there will be more data available. Also, we can better represent AAT only lanes. We considered AAT only links. If you look at our study area, that can be better represented by AAT only lanes only. So that's what we did not do. We also analyzed our matching frequency for every 5 minutes. One can go to every minute or even lesser than a minute, but that increases the computational complexities. That's something that in future one can do, or limitation of our study of 5 minutes of interval. And as well as matching and dispatching time interval also can be different. So right now we keep the time interval for matching and dispatching be the same. That's it. I think that's, I took a little bit of more time. This is the last slide. So yes, so we'll be kind of, be more than happy to answer if there are any questions.
Thank you so much, Dr. Mishra, for your interesting and insightful presentation. I think we'll have questions from the audience. Alex, do you have a question?
Yeah,
Please
thank you
go
for the
ahead.
presentation. Oh,
Thank you.
there's a lot of other questions that can come in too. But I was curious if you could clarify what sort of action space you were using. Was it, like, I know you initially mentioned that it was node-based repositioning, then I think you also talked about zone-based. And on another level, is this sort of like an individual, you're training like an individual driver agent? So given where they currently are, where should they go? Or is this more of a centralized training?
Yeah. Juan, would you like to kind of take that? So yeah,
Yes.
Juan will kind of answer this question. Yeah.
Okay, Dr. Mishra, do you mind go back a few slides to the kind of like the methodology section?
Let me know
Yeah.
the slide number if you,
Yes.
tell me where to stop. Which process one? Where is it?
Just a little, yes, this one right here.
Okay.
So the immediate actions of the reinforcement learning is a matrix that is shown in equation 17. So in that matrix, we do have both repositioning and charging. So the matrix, the cell value is from 0 to 1. And that is kind of like the raw value. We need to transfer from the raw value to the real number of repositioning. And we use equation 18 and 19 to do that. So the xij repositioning, that is from 0 to 1. But the real number of repositioning is REPij shown in equation 18. And the reinforcement learning, because the repositioning is in term from zone to zone, so therefore the agent select a vehicle randomly in zone I, and then reposition to zone J, and the destination is also a node that is randomly selected in zone J.
Okay.
In terms of charging, if Dr. Mishra, if you can go to the next slide. Next slide. Yes, the entire thing. So we can calculate the number of vehicles to go to charge at each zone, CHJ, as shown in the last bullet. And of course, we need to rank the vehicle in ascending order of state of charge. So we will, and the vehicle will go to the nearest charging station as shown in the case study area, because like we have kind of like a dictionary lookup for every node, we know where is the nearest charging station. So it will immediately go there. So it's like a deterministic action. Yeah.
Okay, thank you.
So we have,
Yes, please.
I'm sorry, we have a question in the chat section. I'll ask this and then we'll go to the other person, Pengbo. From
Yes,
the
hello.
Hello, maybe just give me a minute. I'll ask a question in the chat section and then you can go ahead and ask your question. So there's a question that says, what kind of data do you use for travel times on the network?
Yes, so in the Anaheim network, we do have the origin, destinations, and the link attributes. So we follow the user equilibrium principle by Wardrop, and we actually do have it's another topic, but we do have an algorithm to calculate link travel time and link flow. And based on that, we can get the travel time data. Of course, like in the real world, we expect kind of like an assumption of travel time.
Yeah. I think just to add one, yes, correct. So if we look into the Anaheim network, there are network properties of like what is the speed of each link, what is the free flow travel time of each link. I think we simply use the BPR function essentially to compute congested travel time in addition to free flow travel time if there are more vehicles being used from one lane to the other. So the travel times, those we consider are kind of standard travel times. Those come inbuilt with the Anaheim network. That's correct one, right?
Yes, that's correct.
Okay.
Thank you for your answers, Dr. Mishra and Han. Penghu, please go ahead and ask your question.
Yes, thank you, Professor. Very interesting presentation. I have a question. Maybe could you go to your slides? I think around 30. You have a table to compare the waiting time for your algorithm, also the annual allocation.
Let me kind of go there. Please stop me where you'd like to.
Yeah. I think it's a table with a lot of numbers to compare.
Oh, okay.
Yeah,
This
yes,
one?
exactly. Yes,
Okay.
I want to ask, here you show the average daily waiting time, but what is the unit? Is second or?
It is minutes.
It's minutes?
Yes.
And then, for example, for the first line on Sunday, the taxi has 7,900. This kind of minutes is for all your taxis?
Yes, for the entire operation day. And well, the wait time refers to the customer.
Mm-hmm.
So
So could
for example,
you give me like intuitionally, like for each customer, what about their average waiting time?
So that would be like the sum of wait time for all customer during like the entire day. So the way that wait time for customer works is if a customer put a request at time T1, but it didn't get any matching, then it's go to time T2, so that is plus 5 minutes because our time interval is 5 minutes. And if the same customer also like cannot be served at T2 but get delayed into T3, then that would be plus 5 is a total of 10 minutes. And if we take the total waiting time for every customer and during the entire day, then we get the average daily wait time. So it's a sum and not the term average is because we compare the Sunday to the next Sunday of week week 1, week 2, week 3, and so on and so forth.
Okay, yeah, I can understand that it's accumulate time for all the system for one day. But I'm curious, like do you have any information like for each passenger, how many minutes they should wait? You know?
Yeah, good question. So Juan, the question is that like
Okay.
not necessarily.
Yeah, I mean, if you have the accumulated waiting time and you also know how many orders you have for one day, then you can have an average time to show it directly. Sorry, yeah, I just want to have some directly information. But
No. Great question. So do you know on an average how many number of users, Juan? Like then, if we divide this average number by number of users, then we'll get, what the answer to the question is that per person, how much would be the minutes of waiting time?
Yes, and I know that your dispatching time interval also for the rebalancing time interval seems like 5 minutes. So does that mean if you put it as a 5 minutes, it will also increase the waiting time? Like just as you said, if I at the first T1, maybe I'm not matched up with anyone, then I have to wait at least 5 minutes.
Exactly. So that is one of the limitations that we mentioned in the concluding slides. But yeah, if the time interval is extended larger, then if a customer is not served, then he will have to wait into the next time step in order to be considered in the dispatching process.
Yes, I know you run it on reinforcement learning. It asks you for maybe a relatively longer time to compute. So you need like 5 minutes.
Yeah.
So you choose 5 minutes just because for the repositioning and this part you should have this, but for the match actually you don't have that, right? You don't have to do it in such a long time interval.
Yes, so that is what we're working on too. Is we want to have different time intervals, one for matching and dispatching, and one for repositioning. Right now, of course, it's still an ongoing work because like having the same interval is easier to formulate and train. So that's why we use that.
Okay, thank you.
Yeah, but it's a good question. I think we need to get back to you about what is the average wait time per customer. We did not answer that question. You asked a good question. We did not answer that. So to answer that, we need to see what is the average number of customers for that day. So we need to get back to you on that. And the comment of the last comment was also kind of really good. What you asked, and that is, I think we talked about as the last limitation, if you see here.
Yes, I just want to ask if this limitation is come from the reinforcement learning, or you choose it just because some other reasons.
For computational complexities, for our ease of essentially not entering into any further complexities, we considered that. But your point is valid. 5 minutes is a much longer wait time. Can you reduce that? Really not have the same time. So something for us to consider in our next work, or we don't have that yet.
Yeah, may I ask an additional question? So you said in your presentation you have the HV only lanes. But what is the why we have this kind of ways that we only have the human drivers can pass, but not the autonomous vehicles?
Yes. Juan, can you answer? Let me actually take to the exact slide, please. Yes.
So I think like we are planning for the very near future of autonomous vehicle integrations. So of course, this figure here is just an assumption, but it essentially is if the roadway must meet like certain requirements in terms of geometric design, like distractions, objects, and those kind of things. If like those kind of things are existed on the road, then the AV like visioning capabilities or routing capabilities can be limited. So well, it's more from like a policy standpoint where the government are going to limit what links you can drive autonomously on. So therefore, like here we kind of just introduce. So this is our assumptions. We allow AV to travel on the blue link, but not the black link. But of course, we can always change that assumption to any kind of model that we want. I wonder if that answers your questions.
Yes. Thank you so much.
Great.
Thank you, Pembo, for your questions. Let's see if you have further questions. You can just unmute yourself, raise your hand, or write down the question in the chat section.
these are all great questions for us to consider. So yes, we kind of, please, we have time. We can answer more questions, yes.
I think there's no more questions. So thank you so much again, Dr. Mishra and Han, for being with us today. It was an interesting presentation, very insightful. And I see you are still working on this. It's a work in progress, and I'm sure it'll be better than this. All the results were really good, but it'll be definitely better than this. And we hope that you can present the improved results for us very soon. Thank you so much again, and thank you everyone for joining this seminar today. Have a wonderful rest of your day.
Yeah, thank you so much. Yeah, have a good day. Yeah, bye.
You too, bye.